Well, I alluded to the Schwarz inequality, which is very easy to show, and I think we actually showed it for the case of a finite vector space. But for Hilbert space, it's a little trickier. We have enough machinery now that we can do that, and we get it in its total glory, I guess. With direct notation, it's the inequality is relatively easy to demonstrate. Uh, I was always taught that this was the Cauchy-Schwarz inequality, but nowadays it seems like they've decided to leave off Cauchy and call it the Schwarz inequality. So it seems like most of the things I read now, they simply call it the Schwarz inequality. But don't be surprised if you see it as the Cauchy-Schwarz. Remember, it was this, and I think I just gave it as to you in one of the previous lectures. If I have two state uh, uh, vectors for quantum states, or really any Hilbert space, then if I take the inner product of u and v, the two vectors, state vectors, and take its magnitude and square it, that's always less than the magnitude of uh, of of the first one, u, times the magnitude of the second one, v. And what I would first say is that you can pick one or the other. If either one of them is zero, I just pick the v, but it's equally true. If it happens to be that is the zero state, then the magnitude, the absolute magnitude of the zero state is zero, and any vector times the zero state, inner product with a zero state, is the zero vector, and so you trivially get this as equality. So if v happens to be, or u happens to be the zero state, then equality, this holds trivially. Okay? So I'm going to assume that we don't have that, and really all I'll need is to pick one of the vectors. I picked v here, and its inner product is not the zero state, and so the only vector that has magnitude, the inner product with itself, equal to zero is the zero state. So this in general is not zero, and it's a positive quantity if you remember for the magnitudes. So it's just that. And if it happened to be that v is already normalized, then this is just 1 over here. If it's not normalized, then we can certainly normalize it. And that's what I did here, was if I assume it's not 0, then I can get a normalized v simply by taking my original state, v, ket v, here, and dividing it by the square root of the inner product, which is, I would just write as this form, which is the square root of the v with itself. Now then, v is not normalized, then this v sub n, and the n here is, I've got a normalized vector. So when I inner product vn with itself, then it's just 1. And now then, what I'm going to do is construct a vector that I'll take the Vn outer product with itself here, and I'll operate on the other vector u, in this case, state vector u, and I'm going to call that u parallel. As we'll see, it actually is parallel to Vn. This is just a number once I've done this inner product. And so u parallel is just some number times Vn, so it's going to be a vector that is parallel to this the vector Vn. And then what I'll do is I'll take that vector, the u parallel here, and subtract it from u, and I call that u perpendicular. And the reason is because it will be perpendicular. So essentially I'm decomposing u into u parallel and u perpendicular, where this first piece is going to be in the same direction up to a constant, but in the same direction as V, and this will be such that it will be orthogonal to it, perpendicular to it. You can actually show that. If I take this V perpendicular up here, as I've defined it, and take the inner product with Vn, so that's this expression, then I get Vn U. I get Vn Vn. Remember, I'm operating on this side with the Vn kit, bra, times this Vn. So that's just plugging this expression, here into this piece here and distributing across. The Vn, well, that's normalized, so that's just 1, and so I just get a vector, or a number subtracted from itself is 0. So the U perpendicular here, by construction, is perpendicular to V, to the vector V. And now then I'll take the norm of norm squared of U. So I'll take U dot U. And U, remember, was the sum of the, well, over here was the sum of the parallel and the perpendicular components. That's this ket. And the bra equivalent, I just take the bra for each one of these. And then I expand that out. I'll get the inner product of this with this here, the inner product of this with this, the inner product of this term with this term, and then finally the inner product of this term with this one here. If you look at these, U parallel and U perpendicular, that's these two terms, well, essentially here, it's this one and then the Hermitian conjugate of it here. I just looked at this one. And write those out, U parallel, U perpendicular. And remember, U perpendicular is this, and U parallel is this up here. And I do those products. So here is U parallel. That's this term here. And this is U perpendicular written out here. And now then I operate on them. So I get Vn complex, U complex conjugate. Vn operating on this one is Vnu. And I get the complex conjugate of this term, Vn operating on Vn. Again, that's just 1. And so pretty clearly this is 1 and these two terms are identical, and so I get back the notation is a decent notation. U parallel inner product with U perpendicular is 0, so one would expect the parallel and the perpendicular one to be at right angles, or to be orthogonal to each other. So altogether then, these two cross terms, this one here and this one here, vanish because U parallel and U perpendicular are orthogonal. And so I simply get these two terms for U, really the magnitude of U squared. It's the sum of its square of its parallel component and the sum with the perpendicular component. Well, all of these are positive. Any vector or state into itself is always a positive number. That's the length squared or the magnitude squared. The magnitude is again positive. The magnitude here is positive. And so what I'll do is I've got this, and it's the sum equal to the sum of these two numbers, but I can certainly drop this one. Yeah. If that's the case, then whatever was on this side, if I drop this positive number over here, then it has to be greater than what was left if I just drop one of these positive terms, and I chose to drop the perpendicular one. I put in what the U parallel is, well, it's this. Well, it really was this expression the way we had it originally, and this expression, and those operate on each other. This is just a number comes through. Vn. Well, remember Vn was normalized, so it's 1. Its length is 1, and I get Vn uh, u bracket squared here. And now then just put in what Vn is. And remember Vn was V divided by the square root of V squared. And so back out of that to this, the square root of V squared just gives me V squared again. And now then I've got U essentially squared, 1 over V squared times this, and multiply through both sides this whole equation here on this side and on this side. I get UU plus the bracket V has got to be greater than or equal to, because I dropped a term here, this bracket, and then I just switch the two. So instead of greater, I'll write these on the other side. And that then is the Schwarz inequality, or as I like to call it, the Cauchy-Schwarz inequality. Really demonstrated in Dirac notation pretty succinctly on the overall scheme of things. You're going to be hard pressed to find a quicker derivation that's valid in these generalized Hilbert spaces of that is the basis of our quantum mechanics.